Hi, welcome to Unit 6.1, Kinetics. This is part 2 of 3. So in this section, we're going to learn about something called rate laws. But before we do, we're going to talk about normalizing the rates so that no matter what species you're measuring the rate with respect to, whether it's a reactant or a product, the values will always be the same. Okay, so you may remember this image from part 1, which shows the concentrations of these three species over time. And remember, we can get the rate, the instantaneous rate, by taking the slope of the tangent line at a given point. And in the last example, we talked about the fact that because the coefficients are different, that their rates are going to be different. Remember, the larger the coefficient, the greater the rate of appearance or disappearance. So for example, when you compared the rate of NO with the rate of with respect to O2, you will see that the rate is going to be twice as fast with respect to NO. So the appearance of NO is going to be twice as fast as that of O2 because it has a coefficient of 2, so you're making more of it. And what we tried to do last time is we took a rate with respect to a certain species. In our example, we looked at the rate with respect to NO2, and we tried to figure out what will be the equivalent instantaneous rate expressions for all three species. So for NO2, this will be the rate expression, and the equivalent one for NO would be the same, except for NO would not have the negative since it's a product, not a reactant. But for O2, since it has a coefficient of 1, it's going to be half the rate of NO2, and sort of to make up for that, we multiply it by 2. And this was just, again, if we wanted to get the rate of NO2 and set equivalent the rate of the other species in the reaction. How did we do that? But let's say, for example, your friend wasn't interested in NO2 and was more interested in the rate of O2. So if your friend were to do something similar, the rate with respect to O2 would just be the derivative of the change in concentration of O2 over time. And so that part would look normal, but then for the rest of it, they would have to modify the rates of NO2 and NO. And they would do that by saying, well, these rates are double that of O2, so let's multiply this by half or divide by 2, same difference. So it all kind of depends when you're looking at rates, what you're taking the rate with respect to, NO2 or O2. And that can be a bit confusing. So sort of to eliminate all that, we sort of normalize the rates. So it can be respect to any reactant or any product and still be equal. And the way that we normalize the rate is we take the rate expression for each species and then we divide it by its coefficient, or the way I'm writing it here, multiplying it by the reciprocal of its coefficient. So for example, the rate with respect to NO2, which is given here in green, since it has a coefficient of 2, I would divide that rate by 2 or multiply it by the reciprocal to 1/2. The same thing for NO. Its rate expression here is in blue, and then again, to normalize it, I would divide it by its coefficient with 2 or multiply it by its reciprocal. And for O2, since it has a coefficient of 1, it doesn't change. So it turns out that the normalized rates as shown here are the same as the rate you would see with respect to O2, and that's only because O2 has a coefficient of 1. So at any rate, you see what I did there? So at any rate, these normalized rates are what we're going to be using moving forward. But if you're asked a specific question about if the rate of NO2 is this, what's the rate of O2, then you would go back to what we did in part 1. Okay, so now let's talk about something called rate law. So here's our reaction that we saw on the previous slide. A rate law is this expression here, rate is equal to K times concentration of NO2 to the power of N. And we're going to break this down in a moment. But first, let's find out what a rate law is. It's also known as a differentiated rate law. So this is the normalized rate with respect to NO. Remember, we took the derivative there, and we multiplied it by the reciprocal of the coefficient, or the 1/2. And this is another way of expressing the rate other than the change in concentration over time. So in part one, we saw the rate is change in concentration over time, but we can also use this rate law expression to express the rate. So both of these are equal to the rate. And it quantifies the relationship between the concentration and rate. So remember, you may not remember, but from part one, we looked at the very first rate curve we looked at. We saw that the tangent line, the red tangent line, was different from the blue tangent line. And that's because the rate changes over time. And that's what the rate law is helpful for us to know, like at a given concentration, what the rate would be. Because remember, concentration is one of the 4 factors that can change rate. So as the reaction proceeds, if you have an increase or decrease of a species, the rate of the reaction will change. So again, this section is our rate law, and it is equivalent to the rates that we've seen before. So what are the parts of the rate law? First, you have the rate constant, K. K has a unit, and that's super important to know. There will be a lot of questions where you'll have to sort of figure that out. N is known as the rate order. And I want to just pause here for a second and show you what sort of numbers a rate order is. So rate orders will, for us, will usually be first, second, or 0th order. And each reactant has a rate order, but also the reaction itself has an overall rate order, and the overall rate order of the reaction will be the sum of the rate order. So in this case, we only have one reactant, so it's just whatever this N is will be the rate order of the entire reaction. But if we had several reactants, we would add all of these rate orders together to get the overall rate order. It's important to note, especially after looking at equilibrium, that N is not the coefficient. So when we do the equilibrium, the big K expression, we will use the coefficients for the reactions as our powers. This is not the case here. So you actually have to find out that rate order experimentally. And you'll see examples of that later. Okay, so now that we see what a rate order looks like, I want you to write a rate law for the following reaction. And my hint for that before I move on is that you don't know certain things, like you don't know the values of the rate orders, for example. So you're going to use variables for any value you don't know. In fact, your entire rate law expression, which should look something like this, all right, will have variables in it. So pause the video now, and when you press play again, the answer will be revealed. Great, so you should have something that look like this. Rate is equal to K times the concentration of NO2, our first reactant, raised to some power. We don't know what that number is, so we'll use a variable. In my case, I use X, maybe you use something else, times the concentration of F2, raised to, again, some power. We don't know what that is, so I use Y, maybe you use something else. So it should look something like this. This is what your rate law should look like. You should have all your reactants in the concentration brackets, raised to some power, and the K in the front. Now, remember before I said that the units are important. And you want to make sure that your units make sense. So rate itself is always measured in concentration per time, so molarity per second, atmosphere per second, etc. And the rate constant is going to be the inverse units of concentration per unit time. What does that mean? So if this is molarity per second, and these are both molarities raised to some power, when you plug in your K, that value should make sure that both sides are equal. That once you plug in K, you multiply those units out, you should have molar per second here and molar per second there. Okay, and so here's sort of an example of what that could possibly look like in the case where A and B are 1, so the rate orders are 1. Then you would have K times mole times molar, so that will be molar squared, is equal to molar per second. When you go ahead and solve for that, you find that the units of K are going to be 1 over molar per second, or molar to the -1 and second to the -1. Okay, so let's see if you can try this. The CFU is not written there, but it's actually sort of feeding off of the previous CFU. So I want you to find the units for the rate constant. Remember, the rate itself is going to be in molar per second. So my hint for you for that, and how in terms of how to solve that, I would plug the units in. So you know the concentrations of NO2 and F2 are both going to be in molar. Plug those in. And I'm telling you that the rate orders of NO and is 2 is 1, so that will be a 1 here, and then F2 is 3, so that will be a 3 here. When you plug that in, then you're going to isolate and solve for K, and that will give you the units for K. So pause the video now, and when you press play again, the answer and work will be revealed. Okay, so here's what the work looks like. When we plug those values in, we get molar per second equals K times molar to the 4th power. Then I would divide both sides by molar to the 4th power. Molar divided by molar to the 4th power will get me 1 over molar cubed. And the S, or the seconds, are already in the denominator, so I'd multiply those together. So it's 1 over S times molar cubed, which is equal to S to the minus 1 and times M to the minus 3. Anything in the denominator will just have a negative, will have its negative power. So this will be the answer here. All right, that's it for this video. Hope you found it helpful. Have a quality day. And we're going on to part 3 next.